All right, mathematicians, because we are dealing with three-dimensional space, we're going to start, we need to make sure that we have a very good understanding of vectors. Now, we've looked at vectors before, so you should have a decent understanding of vectors, but it's always good to have a little bit of review. So we're going to review vectors, and then we're going to do many example problems. And during the example problems, what I'm going to suggest that you do is when the example problem comes, pause the video, try it on your own, and then unpause it to see how you do. Okay, so let's get into our review of vectors. So first of all, there are different types of vectors. The first type of vector that we'll be talking a lot about is a displacement vector. And a displacement vector has two things. It has a direction. Well, all vectors have two things. They have direction and they have magnitude. And a displacement vector, for example, this displacement vector that we have here, and we need to always have an arrow, is it tells us the direction that we need to head. And this is going from LA to Buffalo. And we can tell which direction it's going because the arrow is pointing from LA to Buffalo. So it's in the direction of Buffalo. And it also has magnitude. And one thing that we can see from this map is that, each of these displacement vectors that are drawn have roughly the same direction. In other words, their angle is the same. But the Dallas to Plattsburgh displacement vector is just a little bit longer. So it has which means that it's a greater displacement. It's further from Dallas to Plattsburgh. So this is just a visual demonstration of what a vector looks like, and in this case, a displacement vector, which is looking at change in distance or change in position. So some writing that you need to be familiar with. Typically we're going to write a vector with an arrow over the top. So in this case, we have vector v, which we write like that. So this is our notation for vector. And what about on the right-hand side? What about when you have these double bars? Well, this is just it's a special way of saying absolute value. We have the double bar when it's the absolute value of a vector. But when we're talking about the absolute value of a vector, this is a scalar, and a scalar is a number without direction. So this is only the magnitude of a vector without its direction. So this vector v here has both magnitude and direction. When we take the absolute value of it, it becomes a scalar, which means that it's just the magnitude without direction. All right, so let's think about adding vectors. Well, let's say that we have vector v and vector w. The first thing to discuss is that a commutative property exists for vectors. In other words, v plus w is the same thing as w plus v. All right. Now, there are two ways in which we can depict the addition of vectors. The first way that we have written here, if we're adding v plus w or w plus v, doesn't matter, you have your starting point and you draw out vector v, which goes in the direction of v and has the correct magnitude. And then from the same starting point, you draw out vector w. And then what you do, if we're doing the method where we have the same starting point, Then what we do is we construct a parallelogram. So, and after we construct the parallelogram, our sum vector, the sum of v plus w, is the vector right here, which goes from where we started to the opposite side. And that is our sum of v plus w. What I think, and this method is totally fine. It's a correct method. It gets you the right answer. What I think is a more commonly used method is called tip to tail. And this is what how I will typically draw vectors. So the idea is, you have your vector v. So, if we're doing v plus w, you start with v, and we had the vector like that, and then you add vector w at the end of vector v. So here was vector v, started here, ended here, and now we're going to add w right there. And our resultant vector is just when we fill in the triangle. And this is called tip to tail because we are combining the vectors, the tip of one to the tail of the other. And notice that v plus w here and v plus w here both will, either method that you use will result in same direction, same magnitude. Okay, that's adding vectors. The other thing that we can do with vectors, and well, there are many other things we can do with vectors, but the other thing that we want to be familiar with is called scalar multiplication. So we're not at the place yet where we're going to multiply a vector times a vector, but what we will do is take some vector v, and we can multiply it by a scalar, some constant. This constant value here is the Greek symbol for lambda. All right, so I got a little distracted there, and back in the middle of talking about scalar multiplications. So let me get back in, and just a quick little recap. The idea is that you can multiply your vector by some scalar, and it keeps the same direction, but what it changes is magnitude. Now, I'm going to put a little asterisk here with keeps the same direction because it can switch at 180 degrees. So if lambda is less than 0, if it's negative, then our vector, well, let's just go like this, then our vector v is going to shift from moving in one direction to entirely different direction by 180 degrees. Okay, so what we see here is just a bunch of iterations of our vector v. Our first vector v here, this is what we're starting with. And then 2v is just twice as long, and half v is half as long, and negative 2v is twice as long, but in the other direction. So we can multiply vectors by a scalar. So when we multiply by our scalar, lambda, the displacement vector, lambda times vector, is going to be parallel to our vector. And like I said before, it will point in the same direction if lambda is greater than 0, and the opposite direction if lambda is less than 0. And if let's say we have vector v where it has some magnitude, then lambda times vector v will have a magnitude that's lambda times our vector, which equals lambda, the absolute value, times magnitude of our vector. So let's think about this in terms of an example, because we've got a bunch of letters here. So let's say suppose we've got some vector w such that the magnitude of w equals 10. And now let's think about 5w. So we're multiplying w by a constant scalar of 5. Then the magnitude of 5 times our vector w will equal 5 times 10, which is 50. So this should seem sort of simple, I think. The idea is, you multiply a vector by some number, and its magnitude increases by the same scale. So from 10 to 50, being multiplied by 5. Okay, so we want to be able to take a vector and break it up into its components. And by components, we're talking about the x, y, and z directions. And we know about unit vectors. So I is a unit vector in the x direction. And j is in the y direction, and k is in the z direction. And the idea of a unit vector again, this is a review from BC calculus. So a unit vector has a magnitude equal to 1. Okay. So when we break things up into their components and into the x and y and z, um, we will write their displacement in the x and their displacement in the y direction and their displacement in the z direction as follows. So let's think about a velocity vector. Here's an example of how you might write a velocity vector where v1 is the velocity in the x direction, and v2 is our velocity in the y direction, and v3 is our velocity in the z direction. And it's really helpful for us to break up velocities into components, as you'll see in the numerous examples that we'll be doing afterwards. Now there's two methods. This is the most kind of popular used method of writing a vector. It also can be written as follows. Uh, we don't usually use this method because it looks more like a point, but it's helpful to know how to look at both examples, and I'll explain this in a second. So the z1 value here is, it's the same idea as there. It's the velocity in the x direction, and the z2 is our velocity in the y direction, and z3 velocity in the z direction. This method of writing it in parentheses eliminates the I and the J and the K, but as I said, it can be confused with a point, so we typically will prefer this method. So let's think about resolving 2 points into a displacement vector, and what's key is the direction that we're talking about. So we're going from the point P1 to the point P2. So from point 1 to point P2, we're calling this our velocity vector. And so we look at each of their displacements separately. So from point 1 to P2 in the x direction, we're increasing by 1. So we started at 2, we end at 3, so 3 minus 2 in the I direction. And for our unit vectors I, j, and k, instead of an arrow, we put a little hat, and that's just because they're special vectors. So I hat plus 7 minus 4 j plus 6 minus 10 k. And then if we simplify this, our displacement vector is I plus 3j minus 4k. So pretty simple. The key idea in these vectors is for us to separate the x's and the y's and the z's separately. Um, for those of us who have studied physics, it's really helpful because the different properties of gravity and motion allow or encourage us to treat y values, our horizontal, or sorry, our y and vertical values differently from our x horizontal values, because gravity only affects the y direction. So it's nice for us to split it up into x, y, and z. And there are many other reasons why we like to do that. And so, you know, right now we're just working on writing things into their components. Okay. Now we want to decide whether this vector is parallel to each of the following vectors. Well, for vectors to be parallel, each of these vectors need to be a scalar of v. As long as vectors are scalar multiples of one another, then they are parallel. So if we think about w, vector w, and if we look at its x value compared to v's x value, it looks like it's being that w is being multiplied by, sorry, that vector v is being multiplied by 2. And let's just make sure that that is true. So from 3 times 2 gets us 6. 5 times 2 gets us 10. So this is true. So w is parallel. So if we look at our a, from 2 to negative 1, it looks like we're dividing v by negative 1/2. So from 2 to negative 1, we're decreasing it by negative 1/2. Let's see if that's true. So 3 times negative 1/2 gets us negative 1.5. And 5 times negative 1/2 gets me negative 2.5. So those are true statements, so it's parallel. And then lastly, if we look at b, b does not equal a scalar times my velocity v, because 2 times 2 will get me 4. So if I multiply 2 times 2, it'll get me this 4. And 3 times 2, where 2 is my scalar, and here's my v component. So 3 times 2 will get me 6, so that's true. But 5 times 2 does not equal 9. So therefore, b is not just a scalar times v, so it is not parallel. All right, so we're going to pause the video here or stop the video here, and we'll have some more videos to go with our introduction and review of vectors. What some of the takeaways that we want to think about? First of all, we write a vector v into its components, and that should be a plus. And we can also write it as in parenthetical form. So we, either one of these is okay. What else have we? Well, we have also looked at the idea of scalar multiplication and the idea that anything that's a scalar multiplication will be parallel to our original. We've looked at vector addition, and I think that's pretty much it for right now. So stop this video, make sure to watch the next one that looks at some more properties, and then we'll get into some example problem.